Okay, we have set up a angled slope. We have added a set of coordinates which we're calling x and y, which are now oriented relative to the slope. You can think of it as x or parallel, y or perpendicular. And we've laid down two forces. There's a surface here, so there's a point of contact between this surface and the piano, so that's always a good place to look for forces. And yes, there's a normal force up. There would be a friction force resisting the motion. Again, the motion is going to be along the surface because it's not going to be thrown up, or it's not going to sink into the surface. The surface is resisting the piano, so the motion must be parallel to the slope. And so there's no friction, there's a normal force, and there's this ubiquitous weight. Now, we know so now what's the first question? Yes, except there's another force. There's a man pushing on this, so there's a moving guy pushing on the piano, and it's moving down the ramp. So we know this thing is moving down the ramp, so we don't know what this force is that the guy's applying, but it is moving down the ramp, so, I mean, it might not be a bad guess to think that it's here. I mean, this seems reasonable. So I'm going to put FG, meaning force guy. Or, no, it's called a man, so I don't want this to be confused with gravity. So I'm going to put FM. This is the force of the man. And I'm going to put a question mark here because I don't know which, I'm suspecting it's down, but maybe it isn't. We'll see. We're going to solve for this. And the question is, calculate the magnitude and direction of this push. So here's the moving man. He's pushing the piano. It's moving down. Now, if you want to know how an object moves, you look for a net force. What's the net force on this object? The net force is you just simply add up all of the forces. And then the forces in one direction are independent of the forces perpendicular to that direction. So this is in the horizontal. This is true in the vertical, or in the x direction and in the y direction, in the perpendicular direction and in the parallel direction. So this is along the x-axis, and this is true along the y-axis. There's a net force. Maybe it's equal to 0, but whatever it is, you can calculate it. You just add up the forces in each direction, and that will be the net force in that direction. Now let's think about the perpendicular direction. This block is not it's not jumping up, nor is it sinking down. So I know that in the perpendicular direction, or in the y direction, however I want to think about this direction, the net force must be equal to 0. Because it's not accelerating upwards, nor is it accelerating downwards, so it must be equal to 0. So what are the forces in that perpendicular direction? Well, certainly n is there, and it's pointed in the positive direction relative to my axis, so I'm going to put n. And is there a force? That has to be balanced by something, because it's not accelerating. So what is that something? Now weight is not pulling, weight is pulling down. And watch what I do here, because you will need to repeat this in many different situations. Weight is pulling down, and relative to my axes that I've chosen, some of the weight is pulling against the ramp, some of the weight is holding it against the ramp, and some of the weight is pulling it down the ramp. So what have I done? I've broken up my weight vector into a portion that is perpendicular to the slope, parallel to this perpendicular axis, and so I'm going to label this component the perpendicular weight, and I'm going to label this component the parallel weight. Now this is now a triangle. You've seen these kind of forced triangles before, but it's really important that this weight is the hypotenuse. This component is parallel to n, and this component is parallel to the surface. You need to draw this. Be careful how I've drawn it there, and when you're in different situations, you're going to be drawing, the weight is always going to be down. It's going to have a perpendicular component. It's going to have a parallel component. And you need to be able to bust up this weight into how much it pulls the object against the surface and how much it pulls the object along the surface. Now when slopes are steep, the weight mostly doesn't pull against the surface very much and mostly pulls down the surface. And when the slope is shallow, the weight mostly pulls against the surface and doesn't pull along the surface very much. So depending on the angle, weight is either keeping you against the surface and not moving you along very much, but when it's steep, it's mostly moving you along and not holding you down very much on the surface. So I'd better end it there again.